My name's Dave Lester, and I'm going to talk today about numbers, errors, and chaos. So this is really about the arithmetic systems available on computers which we use for simulation. We're going to begin with some fairly heavy mathematical techniques and approaches, but the lecture concludes with some more practical advice, and finally we drift off towards philosophy. So we're going to discuss the following subjects: the natural numbers, integers, rational numbers, real numbers, the computer number systems, and the implications for modeling neural systems. And the aim at the end of this lecture is that you should be aware of the different sorts of arithmetic systems that are available, have a feeling for some countability arguments, that's how big the sets of these numbers are. I'm going to start with this quote: Die ganzen Zahlen hat die liebe Gott gemacht, alles andere ist Menschenwerk. So really this is saying that we start with the natural numbers or the integers, and all the rest, as you'll see, is actually constructed from these things. This was the big discovery of 19th century mathematics when they attempted to put mathematics back onto a formal footing. So the simplest kind of numbers are the counting numbers, which start at 1 and work upwards. You should be aware that computer scientists usually start at 0 and mathematicians usually start at 1. So there is a question over where we start on this, but in practice it doesn't make too much difference. One implementation of the natural numbers is Peano Arithmetic. So the Peano numbers are either 0, Z, or the successor of some other Peano number, N. And this defines a recursive data type. And as you can see at the bottom of the slide, we can actually implement addition using a recursive function. In the first line, we can see that if you add 0 to a number m, then that's the answer you get. And in the second case, if the number is known to be at least 1, first number, and you add it to m, then you can instead, you'll get exactly the same answer if you add n to the successor of m. So we're gradually building up the successor functions on the right-hand argument and taking them away from the left-hand argument. It's possible to do multiplication and a power function in Peano Arithmetic, and in each case you're just building on the previous function. So you implement multiplication as repeated addition, and you can implement the power function as repeated multiplication. So, how many counting numbers are there? Well, we're going to claim that there's infinitely many of these numbers, and the proof of this is to assume instead that there were just a finite number of them. If there's a finite number of them, there must be a biggest number, call it n, and now by the Peano Arithmetic, if we add 1 to n, we've got a number that's slightly bigger, one more in fact, and so we found a new biggest number. So there is no biggest number. You can always find one a little bit bigger. And that's the contradiction. So there are definitely infinitely many of these numbers. Now I want to have a quick digression on bijections. They're a very special kind of function from one set, S. I've used S to represent the source, to another set, T, which is the target. And so you'd normally write a function as f with a colon, s arrow t. And that's a reminder to me and to you that it takes an argument of type s and gives an answer of type t. And I'm going to try and remember to use the Greek symbol phi to represent my bijections. I'm not sure why, it's just one of those conventions. The key property of bijections is that they map one element from the source set to one element of the target set and vice versa. So it's a 1-1 mapping. Because of this 1-1 mapping property, for every bijection there's actually an inverse function which takes you back again. from the target to the source. And it has the following three properties. The inverse function is itself a bijection. It is a left inverse, that is, if you first do the bijection phi and then do the inverse bijection, you get back to where you started from for everything in the set S. And it's also a right inverse, that is, if you first do the inverse function on something of type t and then do the bijection phi, you'll get back to t again. And an important property, the reason in fact at the moment that we're looking at bijections, is that if there's a bijection between two sets, A and B, then you can you say that these two sets have the same cardinality. Now, that's not too interesting in a way, because if the sets were finite, then all we're simply saying is they must have the same number of elements in them. The interesting situation arises when we have infinite sets, and now we're able to establish mappings between the two infinite sets with the idea that we can say whether one is bigger or not than the other. So, that was the natural numbers. Now we start looking at integers, and here we're going to include negative numbers and add them into the numbers set that we've already got. This actually has the effect of causing the integers to be an abelian group. By this we mean that the set of values is z, the 0 is the identity element, and the operator is plus. And the idea of the 0 here is that 0 plus anything is the same number again, so that's why it's the identity element. Here are the properties of our abelian groups. You have a left and right identity operation for the plus, which is 0. You have the associativity property, that is, if you bracket things to the left or to the right, it gives you the same answer. You have an inverse, that is, for every number, there is another number which, when added to the first number, gives you 0. And of course, in this case, we simply choose minus x. And it's commutative. That means you can switch the order of the operations around. Now we're going to count the number of elements in this set. We say that a set is countable if there's a subset of the natural numbers and a bijection between the set A and this subset. So A is countable if there is a subset of the natural numbers and a bijection between A and B. If B is infinite, then you say that A is countably infinite, and if there's no bijection, then the set is uncountable. So, with that, we can also establish an enumeration of a set. And this means that if the set is countably infinite, then we can start indexing them using the natural numbers. So here you can see I've indexed the set starting at 0, which shows that I'm a computer scientist and not a mathematician. And the proof that this is possible is simply that the inverse of the bijection exists. You can invert on the natural number n, and you'll get an element in the set. And of course, because the bijection exists, we know that we're actually going to hit every single member of the set capital A. Now, what we're going to show here is actually that the two sets are the same size, or have the same cardinality. They're both, in fact, countable. So we've added what looks to be twice as many numbers to the set that we started with. The natural numbers are the numbers running from 0 upwards, and we've added all the negative numbers in. But the argument we're making here is that there is a bijection. That's a mapping from the integers to the natural numbers, which is 1 to 1. Now, I'm not going to show you that this is 1 to 1, but I assure you it is. So the bijection phi here takes the non-negative numbers, that's I bigger than or equals 0, to 2i, and the negative numbers are taken to minus 2i minus 1. So the non-negative numbers go to even numbers, and the negative numbers are mapped to odd numbers, which is why they're one-to-one, we're missing. Now here's the third mathematical form of numbers, the rational numbers, and in this one we permit ourselves to represent things as fractions. Formally, what you need to do is ensure that the denominator is non-zero, and usually you'll pick it to be positive, and the numerator is an integer. Now this is also an algebraic structure, and in this case it's a field. And the reasons I'm writing these down is that it reminds me to explain what all these things are. So an algebraic structure is a field if you have an additive abelian group, so that is 0 and plus form this commutative or abelian group, just as we had before. There's a multiplicative group, which is that if you omit the 0 element, then you can use 1 as the identity and multiplication, which means, of course, that the inverse element is 1 over the original number, and that's why we've omitted 0. You can't do 1 over 0. So you get those two properties. Again, there are abelian groups. And finally, there's a distributivity property, which is that if you multiply x and y plus z, then you can split the multiplication into 2. So those are the properties of a number field, as it's called, or a field. Again, these are properties. You can use the associativity, the commutativity, and distributivity operations on any rational number, and you'll get the same answer. Rather surprisingly, there is actually a bijection that maps pairs of natural numbers to a single natural number. What we're doing here is using the 2 to the n to represent an even number from which we can extract the first component, n, and we then use an odd number, 2m plus 1, from which we can extract the second number, m. Again, I'm not going to demonstrate that this is a bijection, I merely assure you it is. And using that, we can actually now show that the rational numbers q are also countable. So there's a 1-1 mapping between the previous sets of numbers we've used and the rational numbers. So first we map the numerator to a natural number n using the bijection we used earlier for showing that integers are countable. Then we can use phi x to map this n dashed and d minus 1 to a natural number m. So we've got a way of mapping any rational to a natural number. So far, we've been very mathematical about things. But what are the computer science implications? Well, there's good news. All of the number systems that we've discussed so far are available on your computer, probably. If you use C or C++, then the GMP library is available for download from the GNU website. And it has 3 sub-packages, GMN for natural numbers, GMZ for integers, and GMQ for the rational numbers. Even better news, if you're a Python user, is that the Gimpy2 package is available to you, and this makes available at a Python level the GMP package that's running underneath at C. Do be warned, however, that these libraries are much, much slower than usual computer arithmetic. On the other hand, if they deliver an answer, then the answer is probably correct. These packages have been well checked, and although it's possible there are still issues, and especially if there's an upgrade to a 0.0 version, you need to be cautious, but in general, these packages are going to be very effective at delivering the right answers. So, as you might imagine by now, we're now going to make an extension to the rational numbers to form the real numbers. This time we're going to add the innocuous-seeming axiom of real completeness. and I'm going to go into some detail about this. So a set of real numbers is bounded above if every element of the set x is less than or equal some upper limit y. So y is an upper bound. And then, if it's a bounded set, then there's a least upper bound. There's something in the set x itself, which, or set x of real numbers, which is the least upper bound of the set capital X. So we'll now show that square root of 2 is an irrational number. That is, it isn't a member of the rationals. In order to do this, we'll suppose, on the contrary, in order to generate a contradiction, that square root of 2 is a rational number. If it's a rational number, then there exists a numerator and a denominator such that square root of 2 equals n over d. And this is a proper fraction. That is, there's no common divisor that divides both n and d, because if there was, we'd divide it out. By definition, nd squared, which is square root of 2, must be equal to 2, and of course you can also expand that as n squared over d squared. Now what this means is that the numerator must be an even number, because the right-hand side of the equality is even, the left-hand side must be even. And that means that n is divisible by 2, and therefore you can write n equals 2n dashed. And now, if we put that back into the formula, we get 2n dash squared, which is 4n dashed squared, must be equal to 2 times d squared. Here you'll see I've multiplied both sides by d squared. And again, if you divide that by 2, you'll find that 2n dash squared is equal to d squared, and that means that d has to be divisible by 2. And that violates the condition we laid down in point 2 above here, where we said it had to be a proper fraction. Okay, so we've generated a contradiction here. We said that there would be a proper fraction to represent square root of 2, where you've eliminated all the common factors, and now we've shown that there isn't. And now we'll use this result to generate the difference between the rational numbers and the real numbers. So, now that we know that the square root of 2 is not a rational number, let's consider the set S here. So this is the set of rational numbers such that x squared is less than or equal to 2. And the claim is that this has no rational least upper bound. Well, it's clearly a bounded set. X itself has to be less than or equal to 2. And the proof here is that the least upper bound is the square root of 2, which we've just shown is not a rational number. However, if you look at the second theorem on this slide, if instead we take the values of x to be from real numbers instead of rational numbers, then there is a least upper bound, and it is square root. Remember, the axiom of real completeness said any set which is bounded above has a least upper bound, and that least upper bound will be a member of R. Now, another interesting feature is that the set of real numbers is uncountable, and this is a proof of George Cantor's, which is called diagonalization. So suppose, on the contrary, that R is a countable set, then you would know that there's an enumeration. You're able to draw them out one at a time, and we would have x0, x1, and so on. And you can express these things as decimal expansions. And now we're going to construct a new real number x, which differs from xn at the nth digit. And to avoid problems between the equivalence of 0.9 recurring and 0.0, we're going to change the digits d in the range 0 to 7 to d plus 1, and the bigger digits, 8 and 9, we're going to make 3 and 4 respectively. So, whatever happens, the digit d is changed to another digit, and therefore this new number which takes one of the digits from each of the numbers x0 up to x1 and so on, up to infinity, is going to be different from xn in the nth digit. And therefore x is not equal to any of the numbers that we enumerated already, and that means that there is no enumeration, that is, that r does not have a bijection to the natural numbers and therefore is uncountable. Now, why were we interested in that? Well, the interesting thing here is that there are countably many computer programs. They're in 1-1 correspondence with the natural numbers. There are uncountably many real numbers. Therefore, some real numbers cannot be represented on any computer, no matter how much resource we have, no matter how much memory or how much compute power you have. You would not be able to write a computer program which would deliver those numbers. So something is missing. I'm now going to take a break from the heavy-duty mathematics and talk a bit more about computer science and practical problems. In computer hardware, there are two sorts of numbers that are available to us: the integer types and the floating point types. Unfortunately, neither of them is like any of the systems we've already seen. So let's have a look at the integer types first and the errors that occur with them. The integer types are limited to a small number of bits. You can think of this as a small number of digits. Only these digits are just a single bit, a 0 or a 1. A 32-bit number can represent up to about 2 billion, plus or minus 2 billion, and the 64-bit numbers are really quite large indeed. The problem here is that you have the effect of wraparound. That is, if you exceed these bit limits, the numbers turn negative on you, and that's quite concerning. So here we have an example where wraparound occurs. We're going to add two numbers together, 2 billion in each case, and if you add 2 billion to 2 billion, rather surprisingly, you get minus 294,000 and some other digits. This usually comes as a shock, and if you've done any computer programming, you will probably have made this mistake at least once, whether you noticed or not. The behavior here is the cause of many bugs in computer programs, so just be aware of this. One trick, by the way, for debugging this sort of thing is again to use the GMP algorithms to work with number systems which are absolutely correct, and then observe and see whether the numbers that are being developed with your 32-bit integers are the same as the ones that you should be getting as compared with the GMP calculations. Floating point types are the other sorts of numbers that are available on a computer, and this is implementing a subset of the rational numbers. The most frequently encountered types are float, which has 23 bits of mantissa and 8 bits of exponent, and double with 53 bits of mantissa and a 10-bit exponent. So just for comparison, the float has about 6 decimal digits in it and can represent numbers up to about 10 to the 15, and the double precision has about 16 bits of 16 digits of representation and can represent numbers up to about plus and minus 30, 10 to the 30. It often comes as a surprise that floating point numbers do not obey the properties that we were talking about earlier on, and that it is sometimes possible that x plus y plus z gives a different answer depending on which order you do the additions. Here's the typical example. If we take x to be 1 times 10 to the 30, that's what the 1e30 notation means, and y is negative 1 times 10 to the 30. So those two numbers have an absolute magnitude which is really quite big and close to the limit of what's representable. And then z here is a very small number, which again is close to the limit of what's representable as 1 times 10 to the minus 30. So that's 0 point, and then 30 zeros, and then a 1 at the end of that. And what happens is that x plus y is 0, because the two numbers cancel out, and y plus z is y. And the reason for that is that the z value there is so small that when you add it to y, it makes no difference. Y remains unchanged. So in that's accounting for why these two give different answers. In the first case, you get 0 plus z, which is just a very small number. And in the second case, where you add y to z first, you end up with y, and that just cancels with the x, and you get 0. And so you've got two completely different answers depending on which way you add these two numbers together. This behavior is called cancellation and is also the cause of many bugs in computer programs. Now, it may seem that that cancellation problem was a bit artificial. So here's a practical problem that occurs probably quite frequently in much of the code that's being written in the Human Brain Project. Suppose we want to do a dot product operation with two vectors. So a dot product, you simply take the vectors and pairwise multiply them. So the first two elements are multiplied together, then the second two, third, and so on. And then you add the whole lot together. And it's this addition at the end which is going to cause problems if you're not careful. So naively, you multiply them pairwise and then you sum them. But you're going to have to expect some cancellation could easily occur under those circumstances. And the way you can sort this is to actually sort these terms, having pairwise terms, the multiplications, into an ascending order by their absolute value, and then the cancellation effects are cancelled out. The big problem with doing it that way is that you've made your dot product much more expensive. And of course, dot product may not seem like a particularly common operation, but it is actually the way that smallish matrix multiplications are likely to have been performed, say up to about 20 or 50 by 50 matrices. If you're doing a matrix multiplication, it's highly likely that it's using a dot product underneath, and the question would arise, are they doing it properly or not? So, where does this take us? I'd like to emphasize numerical analysis. This is the discipline that was invented by Wilkinson when it became apparent that the very early numeric computer programs that were written for the Manchester Mark I were actually delivering wrong answers. So this is dating from the late 1940s, and problems were apparent even then. I usually advise my computer science students that they are not qualified to use floating point types. However, usually numerical analysts are not experts in software engineering either, and that's something of a conundrum. So who should be writing this code? Well, actually, of course, it's a collaborative project, and ideally you would want software engineers and numerical analysts to be writing the code together. Now, just to return to an alternative here, if you recall, I said there were countably many computer programs and uncountably many real numbers. So one possibility is to use just the computable subset of the real numbers. Is this possible? Well, yes, it is. I've written an implementation called ERA, which is able to provide you the computable real numbers. I even spent a few years proving this was correct using NASA's theorem-proving tools. Unfortunately, the University of Manchester were reluctant to allow me to stamp on the front that it had been proven correct, so I'm not able to say that. What it does do is allow you to multiply, subtract, divide, take exponentials, logarithms, sines, cosines, and so on, provided that those are well defined. So you can't, for example, take the logarithm of a negative number. The problem with these computable reals is that there's no comparison operation. So you can't determine in a finite time whether the number that you get back is bigger than 0, for example. Or more generally, if you have two numbers, you can't compare them and say which is the bigger of the two. Strangely, you can actually determine the value of the biggest of the two. You just can't say which of the two numbers is the biggest. That's rather odd. And why is that of particular interest to us? Well, the systems that we're modelling in the Human Brain Project are actually hybrid dynamical systems, or at least the very simplest ones would be. You can extend this with stochasticity, that's probabilistic actions, and you can probably add other features to this as well. But a very simple one is the hybrid dynamical system, in which you have a mixture of interacting continuously varying real-valued variables and discrete Boolean signals. So in a particular example would be a system of very simple neurons communicating with spikes. That would be a hybrid system. The spikes are the discrete Boolean signals, either it spikes or it doesn't, and the simple neurons are controlled by continuous real-valued variables. In general, such a system cannot be computable. That is, unless there's some very special properties about the number system that you're actually using, if you go to a general computable real setting, you would need to determine when the threshold voltage is reached on the membrane potential, and that's a comparison operation. And that's not possible in a general computable real setting. So, of course, if the hybrid system was degenerate, everything was continuous, or everything was discrete, then you can probably solve it. But usually this is going to result in chaotic behavior. That is, it depends critically exactly when these actions occur. And I'm defining for these purposes that the a chaotic system is one in which the final state depends on an excessively precise initial state. In other words, to predict exactly where you're going, even if the system was deterministic, requires you to have immensely precise initial state data in order to say whether you go one way or the other. An example of this, by the way, of practical relevance, is aircraft collision avoidance software. The way that works is you're determining whether two aeroplanes are going to approach slightly at an angle or head-on or slightly at the other angle. And if they approach at an angle, then the two aeroplanes can divert quite safely. If it's head-on, you need to know exactly that you're head-on, and then you have to flip a coin, actually, about whether you go left or right. And of course, it's entirely possible that the two aeroplanes both flip the coin and go the same way. So that's actually a system there, and it's because you cannot measure precisely what the angle of approach of the two aeroplanes are. Nothing to worry about. Hasn't happened yet. So a quick way to gauge whether a system might be chaotic is to make small perturbations to the initial conditions and see if there's a large effect on the output. This is perhaps one of the things that is not happening in computational neuroscience, which should be happening. That is, you should perturb your system. You should make small changes to the initial state and see whether you're delivering exactly the same answers or near enough the same answers, or whether something completely different happens. If you observe something completely different happening with very small changes to the input, that's usually a good way of guessing that there might be some chaotic behavior going on. In stable systems, or systems with some kind of stability instead, you would see that if you made small changes to the initial state of the system, you would get approximately the same answer at the output. And that would be a way of checking for the robustness of the results that you're generating with your simulations. One of the things that might then be occurring to you is, so is the Human Brain Project doomed to failure if it cannot use computers to accurately simulate things? Well, I would argue no. What is being shown here is that the limits of computability are simply a reminder that we're making an approximate model of the system. It's not an exact one. And so this even applies to physical model systems like the brain scales system, where again, making an accurate comparator circuit, you can make them more and more accurate. They just take more and more time to resolve themselves as to whether it's yes or no, or whether one is bigger than the other. So these two have an approximate feel to them as well. So in conclusion, we've had a look at different number systems and their computer implementations. We've used bijections to argue about the countability or uncountability of these sets of numbers. We'll return to this in the third lecture when we look at the halting problem. And that's it. Thank you.